Hello, PharmaDG College subscribers. Welcome to another enlightening episode. Scientific Content Lead, Professor Dr. A. Jerad Suresh. Principal, Sri Ramachandra Faculty of Pharmacy. Sriyar Du, Por Chennai. Visual Editing, Ms. Reshma Devi Senthilnathan. Research Scholar, Department of Pharmacognosy. Sri Ramachandra Faculty of Pharmacy. Sriyar Du, Por Chennai. In the vast microbial world, bacteria constitute approximately 90% of the Earth's total microbial biomass, playing diverse roles from ecological balance to disease causation. Among pathogenic bacteria, gram-positive and gram-negative species pose significant clinical challenges. Gram-positive bacteria, thick peptidoglycan walls, but no real defense against powerful antibiotics. Methicillin-resistant Staphylococcus aureus, MRSA, is a notorious gram-positive bacterial strain that appears in grape-like clusters under the microscope. What makes it particularly dangerous is its ability to evade beta-lactam antibiotics, including methicillin, penicillins, and most cephalosporins, thanks to a special gene called MICA. This gene produces a modified penicillin-binding protein, known as PBP2A. Unlike normal PBPs that antibiotics target to disrupt bacterial cell wall synthesis, PBP2A continues to function despite the presence of these drugs, allowing MRSA to grow and multiply unchecked. This resistance mechanism has made MRSA a formidable threat in both hospital-acquired, HAMRSA, and community-acquired CMRSA infections. In healthcare settings, MRSA can lead to severe complications such as bloodstream infections, surgical site infections, and pneumonia, especially in immunocompromised or postoperative patients. CMRSA, by contrast, affects otherwise healthy individuals and typically presents as skin and soft tissue infections, including boils, abscesses, cellulitis, and in rare cases, necrotizing fasciitis or osteomyelitis. The rising incidence, therapeutic challenges, and high morbidity associated with MRSA infections have urged the development of more advanced antibiotics. In contrast to MRSA, which is a gram-positive threat, Pseudomonas aeruginosa represents a formidable gram-negative pathogen, known for its intrinsic resistance and adaptability, largely attributed to its thick outer membrane and robust efflux systems. But Pseudomonas aeruginosa? It's in a league of its own. A triple-layered defense, an outer membrane packed with barriers, super-efficient efflux pumps that eject antibiotics, and worst of all, a biofilm fortress. This bacteria clings to surfaces, forming biofilms that shield it from drugs and the immune system. But to defeat this menace, a hero emerges, Cephalosporin. He is known as CEPC, short for Cephalosporium acridum. No villain is he, nor acrimonious, despite what his name may suggest. His story is one of family, chemistry, and a shared mission. A relentless pursuit to combat resistant bacteria and restore hope in the fight against infections. He hails from the beta-lactam family, alongside his famous cousin, penicillin. Though both battle bacterial invaders, their structures set them apart, giving him unique strengths in the fight against resistance. Penicillin wields a beta-lactam ring fused to a thiazolidine ring, while CEPC carries a dihydrothiazine ring, a six-membered twist that shifts his key modification from position 6 to position 7, granting him a distinct edge in the battle against resistant bacteria. This small shift grants his greater resistance to beta-lactamase, allowing his to persist where penicillin sometimes falters. Through science, CEPC have evolved, birthing generations of powerful cephalosporins. Through the power of science, he have evolved, birthing 5 legendary generations of cephalosporins, each stronger and more adaptable than the last. His journey, however, began long ago. In the ancient world, a humble mold named Cephalosporium acrimonium was discovered in the sewage waters of Sardinia by Italian scientist Giuseppe Brazzu in 1948. From its wisdom, CEPC was born, the first of his kind, a guardian against deadly bacterial invaders. But his early strength was limited, and his path to becoming the supreme defender of the human realm had just begun. At the heart of his power lies his beta-lactam ring, a bicyclic fortress that gives him the strength to vanquish bacteria. At position 4, he bears a carboxyl group, his anchor in battle, allowing him to bind to the enemy's PBPs, penicillin-binding proteins, and dismantle their defenses. No bacterial foe can escape his grasp. At C7, he forged a shield of acylamino substitutions. He gained amino groups at alpha and alpha-1 positions, granting his stability for oral combat. He adopted methoxyoxim, shielding him against the treacherous beta-lactamase. He enhanced his acylation skills, widening his attack range against various bacterial foe. His sharpened molecular arsenal at C3. A benzoyl ester gave his greater absorption and activation. He replaced his C3 acetoxy group with azide, pyridine, imidazole. Extending his survival with aromatic thiols, he gained the power. The first generation, the Knights of the Old Order. The first warriors, cephalexin and cephadroxyl, rode into battle against gram-positive enemies like streptococcus and staphylococcus. Their weapons were simple yet strong, but they struggled against the sneaky gram-negative foes who hid behind their thick outer walls. Learning from past battles, the next generation of warriors cefuroxime and cefoxitin upgraded their armor. Cefuroxime, adorned with a furan ring at its core, bore the methoxyamino side chain, a mystical enhancement that granted it resilience against enzymatic attacks. Alongside this, the carboxyamide side chain fortified its defenses. Cefoxitin, a fierce warrior clad in the power of a thiophene ring, carried the methyl side chain, a mark of its own specialized fortitude. Like its ally, cefoxitin was also reinforced by the carboxyamide side chain, making it a formidable guardian of bacterial resistance. The bacterial armies evolved, summoning even more powerful beta-lactamase spells. But cephalosporins' warriors were ready. The third-generation champions, ceftazidime and ceftriaxone. The oxamino group served as an impenetrable shield, granting beta-lactamase resistance, ensuring the warriors could not be easily destroyed. Their aminothiazole ring acted as a master key, unlocking the gates of gram-negative strongholds, allowing deeper penetration into enemy lines. Among them, ceftazidime, wielding a pyridine blade, was a specialist in slaying the formidable Pseudomonas aeruginosa, striking with unmatched precision. Meanwhile, ceftriaxone, infused with the mystical thiotriazonidian core, possessed an extended half-life in injection, allowing it to endure prolonged battles without reinforcement. Together, these champions redefined the war against infections, turning the tide in favor of science. The cybernetic soldiers of the new age. With the bacterial kingdom rising in power, a new breed of warriors emerged, cephapime and cephborome. Fourth-generation cephalosporins, such as cephapime and cephborome, share a common group featuring an aminothiazole ring with an oxamino. This structural modification enhances beta-lactamase resistance while improving penetration through gram-negative bacterial membranes. Cephapime possesses a pyrrolidinium ring at the R2 position, which contributes to its increased stability and efficacy against resistant bacteria. In contrast, cephborome contains a quinolinium ring at R2, further enhancing its antibacterial spectrum and pharmacokinetic properties. The R3 position in both remains unmodified. These distinct structural features collectively provide fourth-generation cephalosporins with broad-spectrum activity, superior porin penetration, and heightened resistance to bacterial enzymatic degradation. The fifth-generation cephalosporins are the most advanced, designed to tackle multi-drug-resistant bacteria, including MRSA, methicillin-resistant Staphylococcus aureus, and resistant gram-negative strains. In the ever-evolving battle against resistant bacteria, ceftaroline and ceftobiprole emerge as formidable warriors of the fifth-generation cephalosporins, each armed with unique structural modifications that enhance their potency. Ceftaroline wields a 1,3-thiazole ring with a phosphono group at R, granting it superior binding to bacterial targets, while its aminothiazole R2 group, adorned with an oxamino moiety, fortifies its defenses against beta-lactamases. Ceftobiprole, on the other hand, carries a pyrrolidinone ring at R, enhancing its stability, yet shares the same aminothiazole-oxamino R2 configuration, reinforcing its resistance profile. With a simple hydrogen at R3. The highlights: first gen, cephalexin, cefazolin gram-positive. Modification: basic beta-lactam, unchanged dihydrothiazine ring. Second gen, cefuroxime, cefoxitin, H influenza. Modification: add methoxyamino groups, beta-lactamase resistance. Third gen, ceftriaxone, ceftazidime, CSF Pseudomonas. Modification: polar side chains, CNS penetration. Fourth gen, cephapime, broad spectrum. Modification: zwitterion structure, gram-negative permeability. Fifth gen, ceftaroline, MRSA, PBP2A. Modification: side chain with affinity for PBP2A, active against MRSA. Thanks for watching.